So thus far, we have seen the solutions of Schrodinger equation as they apply to what are called bound states, right? So bound states are those that are characterized by the feature that the wave function goes to 0 as x goes to plus minus infinity, right? So an example of a bound state would be something like psi of x equals a to the minus lambda mod x. This function goes to 0 at both plus minus infinity. So bound states are also characterized usually by discrete spectrum, and this is because the boundary conditions imposed usually restrict the values of these lambdas that the wave function can possibly take. And since these lambdas also feed into the energy equation, usually the spectrum is quantized, right? So that is where the initial quantum mechanics comes from. But those are not the only possible solutions of the Schrodinger equation. There can also be unbound states or scattering states. Scattering states are non-normalizable states, and these exist as bound states. Sorry, these exist as solutions of the Schrodinger equation. Of course, to construct a physical solution, we have learned that we have to make what are called wave packets, right? So a non-normalizable state is the momentum eigenstate that you have seen thus far, right? Okay, notice that both the psi of x written above and below can occur as solutions of the Schrodinger equation. When I say Schrodinger equation, of course, I mean time independent Schrodinger equation here. And of course, to tag on the time dependence, you simply have to tag on the factor of e to the minus iet over h bar. That's it. Okay. So let us take a look at scattering states in this lecture and possibly the next. The plan is, I'm sure you have studied some basics of scattering. We will quickly revise what you have already done. And in the next lecture, I will introduce what is called the scattering matrix. This is all working in one dimension. And I'll derive certain important properties of the scattering matrix, the fact that it is unitary. And then we will generalize all these concepts when we study scattering in 3 dimensions later in the second semester, particularly time-independent perturbation theory and so on and so forth. Sorry, not time-independent perturbation theory. Scattering theory we will study as a standalone subject in the next semester. But in this semester, I simply want to give you a flavor of what the scattering matrix is. But before we move on to the notion of scattering matrix in one dimension, I want to tell you briefly about the setting up of the scattering problem, something that you might have already seen in terms of reflection and transmission coefficients. Okay, so what is the scattering problem? The scattering problem is this. Suppose if you have a bunch of particles and you throw a bunch of particles, let us say from the left, okay, scattering from the left. Okay, and you throw a bunch of particles here. Okay, and then the particles travel for some time in free space meaning there is no potential, there is no force acting on the particle, but there is a small region in space that is somewhere over here where there is a force field, right, where the potential is actually non-zero. And after the small region in space, the particles are again free to travel, right? There is no potential. So this is the typical setup of the scattering problem, right? The particles come together, the particles move freely, and then they encounter some force in some localized region in space. And then after some time, the force drops off to 0, and then the particles keep going. It looks like a very artificial setup, but notice that this is perfectly possible and perfectly practical because most forces actually fall with distance. For example, the Coulomb force, it falls like 1 over r square, right? So any known force actually falls with distance. There is actually one force that we know that doesn't fall off with distance, but we don't have to worry about that particular force. That is called the strong force, right? It is described by a theory called quantum chromodynamics. And that is a very weird kind of force where the particles actually start interacting stronger and stronger as you make the distance between them go higher. Okay, so this is why you don't see a free state of quarks. You see quark anti-quark bound states. Anyway, so barring that particular strong force, every other force in nature seems to fall off with distance. So this is a perfectly reasonable picture wherein I can assume a localized region in space where the particles are acted upon by some kind of a force where the potential is of course non-zero, and then particles come into this region freely and then go away from this region freely. So how should I actually do this problem, and how do I actually do this? There are two different statements. The way you actually should do this problem is by saying that, look, in the region, so usually you call this region 1 and region 3, and this is region 2. This is what most books on quantum mechanics follow. And almost all books on quantum mechanics tells you that in the region 1 and region 2, the solution is of the form e to the plus minus ikx. And in region 2, you have to solve for the Schrodinger equation by looking at what the actual potential is. And this usually gives you the right answer. And this is what we'll also do in this class. But before I actually do this, I want to point out a caveat in this way of doing things. In this way of doing things, remember that we are actually, when we say the solution is e to the plus minus ikx, what we're actually doing is we are looking at non-normalizable states. So as I've emphasized repeatedly in this course, these are not physical states that are there in the Hilbert space of the system. So the reason you use and you happily use this non-normalizable states when you deal with scattering is because it turns out that when you do the problem correctly, rigorously, the answers you get are identical with the answers you get from this particular methodology. So what is the rigorous way in which you have to do it? The rigorous way in which you have to do it is not to consider scattering with free particle solutions of this kind, but you should actually form wave packets and let the wave packets scatter. So in region 1, you should actually construct a wave packet. Okay. So you should consider a localized wave packet. Now, what does this mean? When I say localized wave packet, I don't mean localized in position, but you have to construct a wave packet that is localized in momentum. Okay, so it should have some mean momentum k0 with a very small dispersion, which means this wave packet would necessarily be highly delocalized in position. And that is all right. Why do we want something that is peaked in momentum? Simply because it is easier to look at solutions that have definite momentum. Okay, because I'm actually interested in the values of momentum. I'm looking at energy conservation also. I have to make sure that the momentum of the wave packet, the energy of the wave packet in region 1 is the same as the energy of the wave packet in region 3, because overall the energy has to be conserved. And since energy in region 1 is basically h bar square k square over 2m, I need to make sure that I construct wave packets localized in momentum space, which means they're highly delocalized in position space. So which means this dynamical picture of imagining this as something that is very narrow, hitting the potential, getting scattered and going away as another narrow wave packet in region 3 is not really valid in position space. Because when you think of these wave packets as being highly local in momentum space, they are highly delocalized in position space. So dynamics is very messy when you think of these wave packets in position space. Okay. So it's as well that we use wave solutions of the e to the plus minus ikx kind. I think it has stopped sharing very early, so I will stop share and reshare again, because I will continue to pretend that these are perfectly valid states which are describing a particle with momentum k. So essentially what I'm saying is that instead of constructing a wave packet that is peaked at some value k0, I might as well consider a momentum eigenstate with a momentum k0 and pretend that this is a physical solution. And the results of my calculation would not be very different from the case where I actually construct the wave packet and scatter the wave packets. Okay. So instead of constructing a momentum wave packet which is peaked at momentum value k0, I will simply continue considering e to the plus minus ik0x as my free particle solutions, even though they are not normalizable solutions, even though they are not physically acceptable solutions, because what I am after is constructing the amplitudes for reflection and transmission, as I will explain. And these answers are independent of whether you do the actual construction using wave packets or simply take non-normalizable states of the forward time. Okay. So this is the point that we have to keep in mind as we do this, because strictly speaking, we have to scatter off wave packets and not just e to the plus minus ikx as every quantum mechanics book tells you. All right. With this caveat, let us actually, let me set up some terminology. So when I will call the wave, I'll call the wave function as psi r as a right moving wave. Right moving. This means this is e to the ikx. Okay. Of course, e to the ikx by itself does not tell you which direction the wave is moving, as you probably well know. To understand which way the wave is moving, I have to tag on the energy dependence also, which is minus IET over h bar. And if I construct this, you would see that this is a wave that is moving to the right with velocity v. Okay. And psi L would be a left moving wave, which means this is of this form, where I simply switch the sign of k. All right. So by the way, if you have any questions, please stop me at any point and ask, or just type it in the chat window, and I'll try to bring the chat window up over here.
Sir?
Yes.
How can adding the energy term make us figure out if the wave is moving towards the right or left?
Oh, so because you know that a sinusoidal wave function, so you know the wave is anything of the form x plus minus vt, right? This is what I call a wave.
Yes.
Okay. So suppose if I take e to the I k x e to the minus iet over h bar, this is equal to e to the ik times x minus e over h bar k times t. Correct? So notice that in this solution, x minus vt travels to the right and x plus vt travels to the left, right? So in this solution, if you recognize that p equals h bar k, right? And then this would turn out to be basically v over 2. And v over 2 and not v, because this is the difference between group velocity and phase velocity we discussed. So this is of the form x minus vt. And x minus vt is a wave traveling to the right. Now, the way you actually show this is construct any function that is a function of x minus vt, okay, and then plot it as a function of t. And then you see, suppose if the wave looks like this, okay, and then basically, if it is a function of x minus vt, you should see if you plot it as a function of v, if you plot the function x minus vt as a function of t, you should see this peak. For example, if you keep track of this peak and this trough, they should be moving this way. And if you construct the same wave, but it is a function of x plus vt instead of x minus vt, and if you keep track of, let us say, some crest and some trough, and you see how the wave is moving as a function of t, and if you actually plot it in your favorite software, you would see that this is moving to the left. Okay?
Yes, sir. Okay, got it.
Okay. So that is why I need to tag on the time dependence, because otherwise the velocity part does not show up. Okay, so I will erase this part. So this is my nomenclature. I will call this as right moving and left moving, even though I will not put in the explicit time dependence. The explicit time dependence is assumed. It is always e to the minus iat over h bar, because that is the that is what the Schrodinger equation solution tells us. Okay. So let me do this particular experiment. So let me first do scattering from the left. So which means I'm assuming that there is some potential region here. I don't care what potential this is. It is just some potential. Okay, where So I'll just write this down, scattering from the left. And my nomenclature is psi L, psi R. This is e to the ikx, and this is e to the minus ik. Okay. So I will construct some potential that is valid in some localized region of space. Okay. Now this is not the actual form of the potential. This is just some region in which the potential is non-zero. The potential can be anything. Okay. And the potential is 0 here and 0 here. And I'm throwing the particle from the left. Okay. So my goal is to set up the formulas for reflection and transmission coefficient. And I will do this by scattering from the left and the right. And then I will use the symmetry of the reality of the potential energy function to establish a relation between these two. Okay. Now, if I'm scattering from the left, I'm making the particle move from left to right, then the solution I should use is the one that is traveling to the right. Okay. Now, classically, what will happen? So if you assume that particles, a bunch of particles is traveling towards this potential from the left along the plus x direction, then the particle can go hit the potential, and some of the particles will not have enough energy to pass through the potential barrier. So some of them might be reflected, some of them can pass through. Right? So these are two separate things in classical mechanics. But of course, in quantum mechanics, there is a probability for the particle to be reflected and a probability for the particle to be transmitted. So if I set up the wave function, or if I set up the solution should be psi r of x should be such that so in the region, let us say, as x goes to minus infinity. So if I look at very far off regions from the potential to my left, then the solution would look like e to the ikx, which is my initial wave that is traveling along the right hand side, plus r e to the minus ikx, where e to the minus ikx refers to the wave that is reflected back from the potential, and r is some coefficient, and r in general is a complex coefficient because these are wave functions that I'm dealing with. This would be the solution in the region very far from the potential on the left hand side. Very far from the potential on the right hand side, my solution would look like some e to the ikx.
Sir?
Yes.
Sir, when we write this this equation e raised to ikx, so at that time do we mean that it is just a stationary wave or particles oscillating at around their mean position?
Very good. See, so this is what I actually told you. So there is a difference between the setup of this problem theoretically and what we actually do in a lab. So if I were to do this experiment in a lab, what would I do? Well, I would take a bunch of particles and throw it, right? So let us say that there is some very strong positive ion in some region, and I'm throwing a bunch of electrons toward this positive ions, right? So there is a strong attractive force. So some of the particles will be attracted towards this potential, they will speed up and then they will go away. And after they go far enough away, of course, the energy should be balanced. So the energy of the particles far enough on the right hand side will be the same as the energy of the particle far enough on the left hand side. Near the potential, something crazy will happen. I don't know exactly what is happening. Okay. So this is the actual experiment. So if I were to formulate this theoretically, I should construct the wave packet where the wave packet refers to a single electron with a very well-defined momentum and hence a very well-defined energy that is traveling from the left. Okay. And then this wave packet will interact with the region in which there is non-zero potential. It will get scattered from this potential. So think of Rutherford scattering, for example, right? And then after some time, the wave packet will travel towards the left, and the wave packet can also disintegrate, and half of it can come back and some of it can go in the other direction, whatever it is. So if I were to set up the experiment using wave packets, each electron is described by a wave packet because wave packets are physically acceptable solutions, which are superpositions of waves, then this wave packet will have a very well-defined momentum k with a very, very small spread in momentum space. But if it has a very small spread in momentum space, it has a very large spread in position space. So I really don't know. I cannot really keep track of where these wave packets are. Okay, so that is a problem in that. But as long as I keep track of momentum, things are fine because I'm interested in looking at momentum eigenstates. So this is the actual setup. So in that setup, I'm looking at wave packets with peaked at some value of momentum k. In this way of looking at it, I'm simply looking at eigenstates. So e to the ikx is the solution for d square psi dx square equals e psi in a region where potential is 0. Again, oh my gosh, this is stop sharing. Sorry, give me 1 second. Okay. So this the solution to this equation is e to the ikx, right? Where k square is 2me over h bar square. The point, so this is a momentum eigenstate. So this should be obvious. Right? This is a momentum eigenstate with momentum value k. So this has a well-defined value of momentum, but the problem is this is not a physical state. Because this is not a physical state because it is not a normalizable state. No, non-normalizable state cannot be physical states. But the point is that if I do the calculation using these non-normalizable states, I have to basically understand how much of the particles are reflected and how much of the particles are transmitted. And the answer to this question seems to be independent of whether I do the wave packet construction properly or if I simply take psi equal e to the ikx. Okay, so this is a technically speaking, incorrect way of doing this, but it seems to give us the right answer, so we won't bother doing it the correct way. So when I use kx, I don't mean peaking or anything. These are states of very well-defined momentum k. These are eigenstates of the momentum operator. So there is no dispersion in this case. Does that answer your question?
Sir, I'm a bit confused because the equation that is representing psi, that is e raised to ikx, that would mean that the particle is oscillating about its mean position, right?
Oscillating about its mean position. Okay, these are basically.
If I take x-axis as its direction of motion, then it would be like the particle is oscillating about its mean position. Now, since it is delocalized in position space.
Again,
Hello?
so please be careful. So when I say it is delocalized in position space, I'm talking about wave packets. So what I'm actually saying is, suppose if we actually construct a wave packet that is, oh my gosh, my thing is really misbehaving today. I'm really sorry about this. So let me check just 1 minute. Okay, it is connected to the same Wi-Fi. So when I construct a wave packet of this form, then it makes sense to talk about mean momentum and the psi being, so if it is a wave packet, it is a wave packet localized either in space or k space. And if it is localized in k space, it has some mean momentum k0 with some small spread delta k. If I look at the wave packet, then this picture makes sense. Mean k0 and dispersion k. Here there is no mean k0. This is an eigenstate of momentum operator. So momentum operator acting on e to the ikx simply gives me ik e to the ikx. So this has an exact momentum k. The point is, if this wave packet which is maximized at momentum k0 with a very, very small delta k is a good approximation to this wave function that has an exact momentum k. Even though the properties of these two are very different. This wave packet is a normalizable solution. The e to the ikx is a non-normalizable solution. But the e to the ikx is an exact eigenstate of the momentum operator p with an eigenvalue k. This is not an exact eigenstate, but it has, we can construct the wave packet such that this delta k is as small as possible. So if delta k, if I construct the wave packet such that this delta k goes to 0, then this becomes a very, very narrow wave peaked at some value k. So I might as well call this an eigenstate of the momentum operator. So in this approximation, the delta k goes to 0. These two pictures sort of, at least intuitively, start becoming similar, even though physically they are different.
Then, sir, how do we say that it is moving forward? The wave packet is moving forward with time.
Wave packet is moving forward with time and not moving forward with time. Those things you can only say only if you tack on the time dependence. So here, this is a wave packet at time t equal to 0, but I have to understand how this wave packet travels in time. So I have to actually solve this equation. Right, where E, this is, or
Sir, that so the thing is that I'm telling that when you write the wave equation above, so shouldn't there you should plug in this time dependence thing?
I should ideally plug in this time dependence, and I should actually write e to the minus IET everywhere. Since it is a constant factor everywhere, I'm as well suppressing it. Because the way I will actually solve this equation, solve for the reflection and transmission coefficients, is by treating it as a boundary value problem, which I will explain in 1 second, and I will make sure that the wave function is continuous and its derivative is continuous across all boundaries. And in all these calculations, the time dependence will drop out, because the time dependence is always e to the minus IET over h bar. There is no plus minus there. Do you understand?
Okay, sir. So the constant that you have written, that isn't time, right?
The second constant? Oh, that is not time. I'm sorry. So this is, yeah. So this is not time. This t is not time. This t is not time. This is some complex number, that's all. Okay, so that was the confusion?
No, I just I just noticed T right now, but the confusion is yeah.
So this R stands for reflection and T stands for transmission. That is the...
Yeah, okay.
So if you want, I can use something else, but it's just convenient.
Capital R or capital T kind?
So capital T I have to use for this, right? So this is...
okay.
Anything else? Anybody? Okay, so I will erase this part. So the setting up of the scattering problem in general is a complicated business. So please ask as many questions as possible. Because the simple-minded way of doing calculations with just e to the ikx and e to the minus ikx, even though most books do it, is strictly has to be justified. The justification is, a simple justification is that the values of R and T that I will obtain would be the exact same things if I constructed wave packets instead. That is all. Okay, so why am I writing the solutions this way? On the left-hand side, there is two components. The e to the ikx refers to the wave that I am first throwing in, right? The particle that I am throwing in. And the e to the minus ikx with a coefficient R refers to the amount of wave that is being reflected back from the potential. That is in the region to the left, very, very far away from the potential. And to the region on the right, very, very far away from the potential, my solution would be T e to the ikx. Again, a wave traveling to the right. Okay. So yeah, so since there is two possible solutions on the left-hand side, the most general solution of the wave is a superposition of these two. That is just linear. Is this clear for everybody? So I'm simply calling this right because I'm constructing the scattering such that I'm looking at right moving waves initially. That is all. So R is the reflection amplitude, and T is the transmission amplitude. Okay. The probability of reflection is of course, the absolute mod of this guy. And the probability of transmission is the absolute mod of this guy. So capital R is called the reflection coefficient, and capital T is called the transmission coefficient. Okay. So the question is, how do I determine the reflection and transmission coefficients? And the simplest way I can do this is by looking at the current conservation equation. So remember that for any given psi, a solution of the Schrodinger equation I can always construct a conserved probability current J of x. If you remember this, h bar over 2mi minus psi d psi star dx. Okay. Now remember the continuity equation. Continuity equation tells you that d rho dt equals minus del dot j, or in one dimension d rho dt is minus dj dx, where in quantum mechanics rho is psi star psi. Now if psi is a solution of the Schrodinger equation, and if psi has a time dependence e to the iet over h bar, rho is time independent, so d rho dt is equal to 0. So for such solutions, dj dx equal to 0, which tells me that j of x is a constant. Okay. Since rho is time independent in this construction, d rho dt should be equal to 0. So my current that I'm constructing in this way should be a constant with respect to space. So the way we can figure out the reflection and transmission coefficients is by appealing to the fact that j of x is a constant. So I will simply calculate j of x in the region x minus infinity, and I will calculate j of x in the region x plus infinity, and I will equate these two, and then that will give me a relation between r and t. So let us actually do this. So in the region, by the way, I'm writing x minus infinity and plus infinity here because in the region very close to the potential, if I'm looking at something like a Coulomb potential or whatever it is, since I'm doing it one dimension, it is not Coulomb potential, but whatever it is, I really don't know what the solution is. It points very close to the potential. That is why I'm constructing solutions very far away from the potential, because in this case, I don't have to worry about what exactly the form of the potential is and what the solution is at this region. Okay. Very, very far away, there is no force, so it has to be free. All right. Why I wrote an x here? Okay. So let us look in the region x goes to minus infinity. In this case, a solution is given by this guy, right? And I'm calculating j of x corresponding to this particular psi. So if I calculate j of x corresponding to this particular psi, what will I get? J of x equals h bar over 2mi. This can be a little complicated. So I'll write this exact solution, e to the ikh plus r e to the. So this is my psi. So psi star would be e to the minus ikx. Remember that r can be complex. So r e to the ikx times d psi dx will pull out a factor of ik and give me e to the ikx minus r e to the minus ikx plus psi d psi star dc. So this would be e to the ikx times ik e to the minus ikx minus r star e to the ikx. Okay. And in the region x goes to minus infinity, you can work out that this j of x would give you something very simple. Okay. And I leave it to you to check this. Okay. Any questions about this evaluation of j of x? Okay. So in the region x plus infinity, the calculation is much simpler because your psi of x is simply t e to the ikx. So j of x is h bar over 2mi t e to the, what was it? Sorry, star. T star e to the minus ikx times ik t e to the ikx minus ik times t e to the ikx t star e to the minus ikx. And this will give me j of x is h bar k over m mod t square. So 1, and this is my 2. And since I've already established that, excuse me, dj dx should be equal to 0, I can easily figure out that if I equate 1 and 2, 1 minus mod r square should be mod t square. But this I called the reflection coefficient, and this is called the transmission coefficient. So this simple calculation tells me that the sum of the reflected and the transmitted should be equal to 1. Okay, this is basically probability conservation. So this is the typical way in which you establish this relation in a very general fashion without actually worrying about what the solution is in regions very close to the potential. Of course, I'm not doing an actual problem where I have to determine what R and T are. We have to determine what R and T are. I have to basically solve the Schrodinger equation in the region where V is not equal to 0, which we can do for very simple looking potentials. But in general, this is as far as we can go. Okay. Now, before we actually start doing it for real potentials, let me actually show you something fun. So instead of scattering from the left, suppose if I had started by scattering from the right. Okay. So scattering from the right. Now you think, what's the big deal? You can do it exactly the same way. And of course, you are absolutely right. You can do it the exact same way, and you will do it the exact same way. I will leave it to you to do it. But I will do it slightly differently to show you something quite easy that you can actually appeal to the reality of the potential to get the answer quickly. So what is a scattering problem in this case? Well, again, there is some localized potential, the same localized potential where V is not equal to 0. And this region V equal to 0. In this region, there is no potential except that I'm throwing the particle from this direction. Okay, so these are particles moving to the left. So I will use the notation psi L, and psi L of x should be, this is the x going to plus infinity region. This is the x going to minus infinity region. In the x plus infinity region, I have a wave that is traveling towards my left, and some of it gets reflected back from the potential. So I'll have two different waves on the x equal to plus infinity region. In the x equal to minus infinity region, there will be only one wave that is traveling to the left. Okay, this is a mirror image of the first case where I had two waves on the left and one wave on the right, because it depends on where you throw the particles from, that is all. So I will call the plus solution as, this case it is e to the minus ikx plus some of it is reflected, and I don't want to use the same r. Of course, we have to establish if it is the same r. So I'll use a different r, r prime e to the ikx, and this will be the solution in, this will be the solution in the plus infinity region. And there will be some amount that is transmitted, and this will be the solution in the minus infinity region. Remember that I'm always using the same k throughout because energy has to be conserved. E is h bar square k square over 2m. So since energy is conserved, it's the exact same k everywhere, both to the left and to the right. Okay. Now I invite you to construct the J. So homework, construct J of x for this solution and establish the relation between r prime and t prime. It's basically exactly what we did previously, just so you get some practice. Okay. Now let us actually try to look at it slightly differently. I want to understand if the reflection and transmission coefficients, if I throw the bunch of particles from the right, should be the same as if I throw the particles from the left, right? Intuitively, it seems obvious it has to be, right? Why should there be a difference in directions? We can actually prove that this is indeed the case. So let me box this equation. And let me box this equation. Okay. And then you can notice that if you look at this guy, psi r, maybe I can write psi r again here. Oops, excuse me. Psi r of x, the way we have written it down, is equal to e to the t e to the ikx as x goes to plus infinity. Excuse me. And e to the ikx plus r e to the minus ikx as x goes to minus infinity. Okay, so this is our psi r. So can we do any trick so that the psi r and psi l start looking very much like each other? If we can do that, then we can easily establish a relation between the coefficients. The trick is recognizing the fact that the potential is a real quantity. Since the potential is a real quantity, the Schrodinger's equation, which is minus h bar square over 2m psi double prime plus v of x psi equals e psi, and since energy is manifestly a real quantity, the Schrodinger equation, if it is valid for a wave function psi, should also be valid for a wave function psi star, because if I take the complex conjugate of this equation throughout, since the potential is real, v star is v, since energy is obviously real, e star is e, so it should also be true that this equation is valid. So if psi is a solution, psi star is also obviously a solution. This is a fact that you probably already know. The second fact that we will employ is Schrodinger equation is a linear equation. So if psi is a solution, then psi plus 5 psi is also a solution, trivially, right? So I will use the fact that if psi r is a solution, then psi r star is also a solution. By linearity, any linear combination of psi r star is also a solution. So suppose if I take the weird combination, let us say 1 over t star psi r star minus r star psi r star psi r. Psi r star is a solution, psi r is a solution. So psi r star minus r star psi r, which is a linear combination of the two solutions, is also a solution. And then just multiplying by 1 over t star because it's just an overall number that doesn't change anything. Okay. So if you look at what is this particular combination, which is also a solution, this starts looking very much like psi L. So psi r star of x minus r star psi r of x times 1 over t star. This wave looks like 1 over t star times 1 minus mod r square e to the minus ikx as x goes to minus infinity. And it looks like e to the minus ikx minus r star t over t star e to the ikx as x goes to plus infinity. So what is it that I'm doing? I am not scattering from the right. Okay, if I look at the scattering from the left experiment that we initially did, and we constructed the solutions psi r for the plus infinity and minus infinity regions, and I'm simply taking I'm simply taking a linear combination of these solutions. If I take a linear combination of the solutions of the first problem, then if I look at this box, it starts looking very much like the box above it. So in the region x plus infinity, I get a wave that is a linear combination of e to the minus ikx and e to the ikx, which is exactly true in the first box. In the region x minus infinity, I get a wave that is e to the minus ikx, which is exactly what I have in the first box, right? So if these two are valid, if the first is a valid solution, then I can simply equate these two coefficients and relate what r prime and t prime should be in relation to r and t. And if I do that, you actually find that t prime should be the same as t, and r prime is actually equal to minus r star t over t star. Okay. What does this mean? It tells you that whether I am throwing the particle from the left or the right, the transmission amplitude is exactly the same. T prime is the same as t. But you might object saying, wait, the reflection is slightly different, but it is actually not different because r prime is equal to minus r star t over t star. T over t star is just a phase, right? So if you write t as some c e to the I theta, where c is the magnitude of t. So, or if you write t as mod t e to the I theta, then t over t star is just e to the 2I theta, which is just a phase. So the reflection coefficients for these two experiments can vary at most by a phase, but the transmission amplitudes are exactly the same. But if they vary by a phase, the absolute square should be the exact same thing. So r prime is the same as r, and t prime, r prime, which is mod r prime square, is the same as r, and t prime, which is mod t prime square, is the same as t. Okay, so the reflection and transmission coefficients should be exactly the same things, whether I am throwing the particle from the left or the right, as long as the potential is the same. Okay, so here I use the fact that the potential is a real quantity and the Schrodinger equation is a linear equation. So by using these two tricks, I can establish that this is true. But if you actually go ahead and if you don't believe me, you do the homework problem, did it in blue here, construct g of x and relate r prime and t prime, and you'll get the exact same relation as above. And then of course, in an actual potential problem, you can do it both ways. You can figure out r and t by scattering from the left, and you can figure out r and t by scattering from the right, and then you can see how the reflection and transmission coefficients in these two cases is related. Okay, so we'll postpone the actual problem to the next lecture, and in this lecture we'll stop at this point. Do you have any questions?